Class problem number 12, in-class problem number 12. It's a max height problem. Well, wait, shoot. I wonder what kind of problem this is. I should have told you this. We should work through the problem types.
Max height.
Okay, so baseball is hit straight up for a pop fly. It takes 2.2 seconds until the catcher catches it. How high did the ball make it? And then with what velocity was it hit? Okay, so there's two parts. Let's ignore it with what velocity. How high did that ball go? Okay, so we're looking at in-class problem number 12. So if we kind of look through this problem type chart, is this a 1D motion problem?
Yes.
Yes. Is it in the Y or X? It's in the Y column. Okay, so which means we can go delta Y, VI, VF, A, T. Okay, it's a 1D motion problem. Is it a constant velocity problem? No, not a constant velocity problem. Is it a free fall problem? Is the only force acting on the ball gravity? Yes, and you can say, but it was hit. You're right, it was hit. But we're not looking at the ball being hit by the bat. We're only talking about the ball moving after it was hit. Okay, so ball was hit, great. It's moving now, right? So what force is acting on that ball once it leaves the bat? And I heard gravity, I heard someone say it. And only gravity. So therefore, it's a free fall problem. So therefore, our acceleration is negative g, and on Earth, g is negative 9.8 meters per second squared. Is the baseball dropped? Or does it fall? No. Is it a max height problem? And the answer is it could be. It could be. Or, and then the last part is it a delta y is equal to 0 problem? And again, it could be. So we just got to figure out what part of this we are looking at. So the question, I guess maybe before, the question being asked is how high did the ball make it? How high did it go? So if we kind of keep that in mind, a quick picture is going to be nice. We have a ball. It's hit straight up into the air. It goes to this thing that we call max height. And at max height, the ball is going to stop. And then what's going to happen is that ball will come straight back down. And we are kind of, there should be a little bit more wording on there. But we're going to assume that the catcher catches it at the same height as the bat. Okay, it doesn't say that. It should have said that. It doesn't say that. But we're going to say the bat is here, the catcher catches it here, we'll just go with it. So this is kind of starts and ends at the same height. Now what I did is I tried to do two different colors to show that like the black is on the way up and the blue is on the way down. They're going to stop and end the same height. So what we really want to do is we want to figure out, well, the question being asked is how high? So we really have three different locations, and I talked about these problems are really dealing with like comparison of two locations. Do we want, so if we just call them location 1, 2, and 3, location 1 is once it leaves the bat, location 2 is max height, and location 3 is when it comes to the catcher's hand. So we're going to compare two locations. Do we want to compare 1 to 2, 2 to 3, or 1 to 3? Or how high does it go? 1 to 2, right? Because what we're trying to figure out is how high from here, what was the distance to that max height? And what variable would represent how high something goes? That's our delta y. Okay, so for the first part of this problem, we're trying to figure out delta y. Then this is a max height problem. This is a max height problem if we're going to compare from it moving up. So now I'm just going to kind of pretend like I didn't draw that blue line. Now I only have the ball going up off the bat to maximum height, and that's all I care about. So it is a max height problem. So if it's a max height problem, we know the velocity at max height is 0. Is that initial velocity or is that the final velocity if we're comparing from the bat to max height?
What'd you say?
At max height, velocity is 0.
Yep.
Is that your initial velocity or final velocity? It's our final velocity, right? So that's the final velocity in this way that we're looking at. Okay, so we don't know delta or VI, that's part 2. And there is a time, okay, and it takes 2.2 seconds. Okay, it does give us a time. Is that the time it takes to get to maximum height, or is that the total time in the air? It's the total time in the air. Okay? So, it kind of is a delta y problem too, or delta y is equal to 0 problem, right? Because if it leaves the bat and it lands in the catcher's hand, we could say that's a delta y is equal to 0 problem. For just a second, let's talk about that. If it takes 2 seconds to go from here up and back down to here, that's a delta y is equal to 0 problem. It takes 2.2 seconds. How long did it take just to go up? Half of that, right? And how long did it take to go back down? The other half. And that's what we put on here is the total time is 2 times larger than the time to max height, is what we put in a delta y is equal to 0 problem. So, the opposite, or the inverse, I think inverse would be the appropriate term, is we could say the time is half that. So it went from here to here to here was 2.2 seconds. So from here to here is simply going to be half of that, or I'll show it. I probably won't do this again, but it's 2.2 divided by, or we'll go times 1/2, right? Because it's 1/2 of that. Now, from here on, I'll probably just write 1.1 second. It's half that. So 2.2 divided by 2, or times 1/2, however you want to approach that. The amount of time it took to get to maximum height is half of it, or 1.1 seconds. Okay? Now, if we go through and we pick an equation that doesn't have an initial velocity in it. What equation does not have an initial velocity in it? Number 1 does, you're right. But is number 1 going to get us the information that's going to give us average velocity, right? And is the ball moving at a constant speed? No, it wasn't, right? It's going to change. So, what equation doesn't have a VI in it? Besides number 1. Because that doesn't fit our list of variables. Does number 2 have a VI in it? Does number 3 have a VI in it? Does number 4 have a VI in it? Does number 5 have a VI in it? Yeah, it does. So, what do we got to do then? There aren't any equations without a VI. So first then we have to, in this case, we have to solve for VI. Now, for the record, there is an equation that does have no VI in it. Like most textbooks don't ever put it in there because it's really close to, I think it's really close to equation number 3. I think I have to go look it up because no one uses it. But instead of it being VIT, it's VFT. But instead of being 1 plus 1/2, I believe it's minus 1/2 AT squared. So it's close enough. It gets screwed up. So in this particular case, there isn't really another way to do it unless we solve for that first. Okay, so we're going to have to do like a double calculation in order to do this, because there aren't any that are set up like that. So, if we solve for, we need one without a delta y now, which equation doesn't have delta y? Equation number 2. So we can say VF is equal to VI plus A times t, where my final velocity at maximum height is going to be 0. So 0 is equal to VI plus negative 9.8 times my t of 1.1. So we get 0 equals VI plus a negative, so I'm just going to say minus. It's going to be minus 10.78. A couple different options on how you solve for VI. You could subtract VI to the other side, and then it'd be the opposite of VI, or negative VI is equal to negative 10.78. You could add 10.78 to the other side. It's really kind of up to you, but if you do your algebra correctly, we get a velocity, initial velocity of 10.78 meters per second. It's going up, positive, up. It leaves the bat at 10.78 meters per second. Now that we know the velocity that it leaves the bat, now I can choose an equation that has a delta y. So we have some choices. We could use equation number 3, because now we know VI, we know A, we know T. We could use equation number 4, VF squared plus V is equal to, VF squared is equal to VI squared, VF squared is equal to VI squared, plus 2 times A times delta y, and we can solve for delta y. Or we could use equation number 5, and we could say VI plus VF divided by 2 times T will give us a delta y. Just don't use number 2 because we already used equation number 2. So 3, 4, or 5, which one do you want to use?
5.
5 it is, all right. So we look at 5, and we can say delta y is equal to VF plus VI divided by 2 times T. Because at maximum height the velocity is 0, what we're left with is VI divided by 2 times T. So delta y is equal to 10.78 divided by 2 times 1.1. And then hopefully we get the same answer that's on our sheet. 5.929, so 5.93. Yeah. So delta y is equal to 5.93 meters. Now is that a positive delta y, or is that a negative delta y? Did it go up? Sorry, keep pulling the camera. Did it go up 5.9 meters, or did it go down 5.9 meters? Up. It went up, so it's going to be a positive. That's a positive. So that is a max height problem. It's a problem that has no initial velocity, and the way our Fab 5 equations are set up have no initial velocities. They all have initial velocity. So in this particular problem, we had to solve for initial velocity first. It's not super common, but it is something that we could do. Okay. Next thing today we are going to do is we are going to do a lab, an activity, I don't know what you want to call it. We're going to calculate your reaction time. So your reaction time is something that we could measure with a stopwatch. And we could say, oh, how long did it take you to respond to some type of stimulus? But what we're going to do is we're going to measure. Okay? So in a minute you can get one of those. You don't need it quite yet. Drew is just telling us that yes, we are going to drop a meter stick. Okay? And if we measure the distance that the meter stick falls, then that's your delta y, and then we can determine how much time that takes in order for that to happen. So you and a person are going to need to work together. You're going to do your own reaction time, they're going to do their own reaction time. But you got to have someone drop the meter stick for you. Because it doesn't work very well if you drop your own meter stick, because you're probably really good at catching it really fast if you know when it's going to get dropped. So the idea is you're gonna hold it at like 50 centimeters, and it kind of depends how you want to put your finger on top, on the bottom, kind of split your two fingers at 50 centimeters, and you're just gonna hold them a couple centimeters apart. And then the person who's dropping it, probably gonna hold it here. And they're gonna say, are you ready? You can say, yeah, I'm ready. And then they're gonna say, okay. And then they're gonna drop it. Okay, notice I didn't drop it right away, because if you say, like, I'm gonna drop it on 3. 1, 2, 3. I'm pretty good. Okay, so the intent is for you to like, just make sure they're ready, and then drop it, and then they have to try to respond, react, and catch it. I was holding my hands here. When you do it, you're gonna wanna rest your forearm on the table, so that way you can't like dip your hand to catch it. So you kind of rest your hand over the edge of the table, like this, and then you just kind of hold your fingers, and then catch it. Every now and then, just put it out there, people say, yeah, I'm ready, and then when it drops, it hits the floor. They didn't react quick enough. It happens, just do it again, and that we'd say wouldn't count. If we start at 50 centimeters, and if it drops, and I catch it at 30 centimeters, how far did this meter stick just drop? What's that? Negative 20 centimeters, right? Because it went down, so negative, good, negative 20 centimeters. But all of our calculations, we have to have units of meters. So remember, meters to, or centimeters to meters, centimeters, 2 decimal point shift, so negative 0.2 meters. Okay? So you're going to do it 5 times. Catch it, catch it, catch it, catch it. Record your times. It's the distance. Now, it doesn't matter. Like I said, I started at 50, I caught it at 30. If I started at 50 and I caught it at 70, it's still a negative 20, right? So it's going to go down. Then you're going to calculate your times. And once you set up your list of variables, I need a sample calculation. So there's a little spot for a sample calculation. But once you get that initial one done, it's going to be the exact same calculation. All you're going to do is change your delta y. If you want to do it, the calculations, there's plenty of room on the back. But a lot of times people just do the rest of them in a calculator. And then there's 2 questions about what's the longest amount of time your reaction time could be to just catch it. So if you started at exactly 50 and it slid and you caught it like right there, we would say 50 centimeters went through the ruler. Your slowest reaction time in still catching it would be if you went 50 meters. 50 centimeters. Then there's a dollar bill example where you have the whole length of the dollar bill, and you can say, well, what could be the reaction time to if you were to hold a dollar bill in the middle, your friend, and they were to drop it, could you catch it in time? So you can do that calculation. And somewhere in here, I have some money that if you want, you could try it, but the intent is a calculation for it. I'll try to find those dollar bills for you, and I'll set those out. For the record, they're photocopied, and they are fake, and I am not trying to pass them off as legal currency. So if I can find them, I'll put them out for you to try a dollar bill if you want. So there's the sheet. There's a couple calculations for you to go through and do, and when you are done with that, you can submit it in Canvas. You are doing your own activity, but you're going to need some help catching it.